Welcome everyone, my name is Dongwook and I'll be your guide to use Wannier functions. And in this presentation, I'm going to tell you some theoretical backgrounds that you need in order to obtain high-quality Wannier functions. So why do we need Wannier functions and why they are so useful? I think you already have very strong motivation to learn this technique because you are already watching this video, but tell you some examples. We can analyze chemical bondings by using Wannier functions. In this example, they obtain sp3 type Wannier function for silicon and gallium arsenide. And you could see here in gallium arsenide, Wannier functions are more asymmetric because of inversion asymmetry in the crystal structure. So by this way, we can get some chemical insight to a solid state system. Another motivation is related to construction of model Hamiltonian. We know that model Hamiltonians provide a very important role in physics, especially to understand some system in a very intuitive way. For example, you can think of Hubbard model. So in order to obtain a model Hamiltonian, we need to have only a couple of basis functions, and Wannier functions can provide a very nice role for such a small number of basis set. The third motivation is that using Wannier functions, you can calculate physical quantities in a very high accuracy in a dense K point. And this is called Wannier interpolation, and I'm going to cover this in more detail later. Anyway, this Wannier interpolation is especially useful when you are dealing with Berry phase related quantities, because Berry phase related quantities like Berry curvature, they rely heavily on fine details of the electronic structure as well as the shape of the Fermi surface and Fermi sea. So this really requires a dense sampling of the K-space, and this can be done efficiently by Wannier functions. Finally, we can use Wannier functions as building blocks for large-scale simulation of the device. For example, you can construct Wannier functions for the lead and conductor and right lead separately, and you can assemble them like Lego blocks. And this really enables us to simulate large-scale device structure in a high accuracy. And this is quite impossible to simulate in a standard DFT calculation code. So what I'm going to cover in this video is a theoretical background and some physical insight that you need for obtaining high-quality Wannier functions. So I'm going to introduce these major concepts like what is gauge degree of freedom and what is gauge indeterminacy, projection, disentanglement, energy window. There are several: outer window, inner window, and frozen window. That might be confusing in the beginning. And also I'm going to tell you what is the Wannier interpolation. And to explain so, I'm going to cover two material examples: a lead titanate for an insulator and iron as a metal. But for practical use, this will be covered in a hands-on session at the end and on the last day of the workshop. So what is the Wannier function? And I guess you already know what is a Wannier function already. Wannier function is defined as a Fourier transformation of the block function. So this was first introduced by Gregory Wannier in 1937. And this Wannier function is localized around Bravais lattice R. Certainly this is not an eigenstate of Hamiltonian, but there is an advantage because this function is well localized in real space. Because for block function, they are quite far spread and periodic, and they are labeled by the crystal momentum K. But for Wannier functions, they are localized around the Bravais lattice R, and the index is Bravais lattice R. So for 0, 1, and 2, they are localized in different Bravais lattice sites. So Wannier functions also have very nice properties, and that's one of the reasons why many people are using it. The first thing is that if you construct a block function like this out of Wannier states, you can easily prove that this satisfies block theorem. And starting from the orthonormality between the block functions, you can also show that Wannier states are also orthonormal to each other. What about the completeness? Well, in principle, if we are dealing with infinite number of Wannier functions, these form complete basis set. However, we always have a handful of Wannier functions at the end of the calculation practically. So you really have to watch out whenever you have to use completeness relation in your theory. Finally, one of the most important properties is that it is localized around the private lattice R. But there is a condition. The condition is that U has to be a smooth function of K. This is simply because of basic properties of the Fourier transformation. So the more and more the function is slowly varying in K space, it is more localized in real space. So on the other hand, if the function is quite varying a lot in K space, then the function is also quite spread in real space. So in order to obtain well-localized Wannier function, it is important that we have very smoothly varying function U. But there is a problem. The problem is that we have intrinsic indeterminacy of the gauge. By the way, gauge is choice of the phase vector in the wave function. What I mean is that if U and K is an eigenstate of the Hamiltonian, another state with a phase vector in front is also an eigenstate of the Hamiltonian. So this really leads to a problem, because if you choose different phase convention for the wave function, we end up having different Wannier function. So in principle, there are infinitely many number of Wannier functions that you can obtain. So let's consider an example. So what I'm going to do is I'm going to start from the original Wannier function, and I construct a block function like this. And I'm going to transform back to real space, but instead I'm going to transform with a phase vector like this, and I define phi equal to cosine k in this example. So the final result is that this one. For Wannier function localized at 0, it is quite localized, but there are more features like it's more wiggly and it's a bit more spread. So the main lesson from this example is that Wannier functions are not really unique, and depending on the choice of the gauge, we end up having some different Wannier function which is poorly localized. And this is also the problem in computer algorithms, because in many cases in DFT codes, we calculate block functions independently for each K points. So there is no correlation of the phase, how they behave in the neighbor points in K space. So this arbitrariness of the phase vector leads to a serious problem in obtaining the Wannier function. So in general, stating the problem again is that when we are dealing with n block functions, we have SUN gauge degree of freedom like this instead of simple phase vector. So there are this number SUN degree of freedom to obtain a Wannier function. So there are in principle infinitely many number of ways to obtain Wannier functions. But the idea is that we choose U such that it minimizes the spread of the Wannier function so that they are really localized. The spread of the Wannier function, we can define it as second moment for the Wannier function like this. And what we are going to do is we want to find U that minimizes this omega. Well, this functional is definitely capturing the behavior in real space, but the major breakthrough was that we can minimize omega in K space. So how can we work in K space? So the idea is that we can express this quantity in block functions like this. For example, the Wannier center is expressed as K-space integral of the Berry connection, and this R square for the Wannier function is given by this quantity, which is also called quantum metric. If you are familiar with Berry phase theory, this has very close relation to Berry phase theory of electric polarization. So just look at this equation. You see that minimizing omega corresponds to minimizing the variation in K-space. So it means that in order to minimize the spread in real space, we just need to smooth the gauge in K space. That's what we are going to do. So in practice, what we are going to do is we start from this expression in K space, and for this transformation U, what we do is we calculate change of the spread with infinitesimal change of U, and we find the steepest direction that minimizes omega, and then we update U in this direction. And we can iterate this process until this change of the spread becomes sufficiently small. That's how we get maximally localized Wannier functions. So this is the workflow that we follow in general. The first thing that we have to do is we first convert the charge density by other DFT codes like FLEUR, and then from this converged potential, we obtain block states. And then we project the finite states onto block states by the following equation. This Gn is the initial guess of the finite function, and we project this onto block states. And the third step is, well, we have these block-like states whose number is n, and then we apply, we find n by n matrix U that minimizes the spread. For minimizing the spread, basically we have this k-space derivative, but because we are working on a discrete k-mesh, so we need a finite difference expression for that, and what we need is this m matrix. So mmn matrix and amn matrix for the overlap and for the initial projection should be provided from the DFT code such as FLEUR. So one example that I'm going to deal with here is ferroelectric lead titanate. It is quite popular material for the ferroelectric phase transition at very high TC, and this is known to be one of the most important ferroelectric and piezoelectric materials for industrial application. Anyway, the band structure looks like this, and I want to emphasize that before doing anything about the Wannier, please analyze the band structure and density of states and their orbital character. So I have done this job, and what I have found is that states here corresponds to lead S states mostly, and these bunch of bands are coming from oxygen P states. And what we want to do is we want to obtain finite function in this energy range for 9 block functions. So the natural choice for the initial projection would be we use px, py, pz orbitals for 3 different oxygen atoms. So that's what I'm gonna do. So then with this projection, you can minimize the spread using finite 90 program, and this is what you get at the end of the calculation. You get omega d and omega od, which are different parts of the spread, and you see the change from the previous step is very, very tiny compared to original value. So you can say that this is well converged. You also get the centers of finite functions and the spreads. And I can also plot the shapes, contour plots for the finite functions, and we can find beautiful shapes of px, py, and pz states localized at the oxygen. So this is the band structure that we started from, and from the finite function, we can also calculate the Hamiltonian and then diagonalize to get the band structure, and that's what we get at the end. So the agreement between FLEUR and finite 90 calculation is very, very nice, meaning that our finite function represents this energy window in a very high accuracy. So basically what we have done is to obtain the tight binding model. The tight binding model assumes a localized states as a basis. So it includes, for example, on-site energy term and nearest neighbor interactions and like second nearest, third nearest neighbor, blah, blah, blah. We can do basically the same thing for finite functions. So we expand Hamiltonian like this using finite functions. And the function in the middle, the matrix element of Hamiltonian with finite function, is essentially is a function of the difference between r prime and r because of periodicity of the system. So, and because the system is periodic, we can apply Fourier transformation like this, and we end up having the Hamiltonian in k-space. So this becomes an n by n Hamiltonian, and n is simply the size of the finite function. And this hk is given by the Fourier transformation of hr that you obtain at the end of the finite 90 calculation. So once you diagonalize this hk, what you get is the band structure as I have done. And in principle, you can also calculate many other quantities. This is the main idea behind the finite interpolation. So the motivation is that in DFT code, there is a limitation. Computationally, it's very difficult to calculate in Q space. So usually we choose a very coarse Q mesh for FLEUR code, like 8 by 8 by 8, or sometimes we go up to 32. but we don't go to like 1,000 to crazy numbers like that. So what we do is first convert the charge density, and we obtain block states, and then we can obtain some observable, let's say FQ, within the block basis. An example of the observable includes Hamiltonian, Pauli matrices, spin torque, orbital and spin operators, orbital characters, and there are many things also. So what we are going to do, what I am currently doing is we want to add more and more routines that people can calculate physical quantities from FLEUR, and then later on we use it for Wannier calculation. Anyway, the second step is we obtain Wannier function in real space, and once you obtain Wannier function, and we get also UQ at the end of the calculation. So we can get an expression of this expression FQ in R space, and in R space expression can be written in this way: simply a Fourier transformation with a gauge transformation matrix U. So once you have done this job, it's almost done, then what you do is you Fourier transform back to K space, but now K is simply a parameter, so you can do it in any arbitrary dense K mesh, and then you can calculate some physical quantity in a very high efficient way in a very dense mesh. So this mesh could easily go up to 500 or 1,000 as long as you have computation power. But how does it work? To be frank, when I heard about this technique for the first time, it sounded like actually a bit of a lie. A reason is that we start from Q space and we obtain the Hamiltonian R space, and we are going back to K space. So it's kind of coming back to this origin actually. But actually it is not. I'm going to tell you why. So what we do is we perform a discrete Fourier transformation in a coarse K mesh, 8 by 8 by 8, for example. And this implies that our function, Wannier function, is periodic in every 8 unit cells. It looks like that in reality. So one criteria for the Wannier function that we have to have is the spread of the Wannier function has to be smaller than the 8 unit cell, the size of the supercell imposed by the choice of the Q point, right? So also a very important remark here is that fine details in K space is correlated with long-range behavior in R space. But our basis set, which is a Wannier function, is very well localized, so there is no problem in describing the long-range behavior. So basically that's why we can interpolate in K space very efficiently. So conclusion is that the Wannier function, Wannier interpolation works because Wannier functions are well localized. So one example is the evaluation of the Berry curvature, and this was first explored by this paper. So in order to calculate the anomalous Hall effect, you have to calculate the Berry curvature. For BCC iron, for example, the Berry curvature usually shows a very spiky behavior. It means that spiky behavior means that we need to sample K space quite a lot in a very dense mesh. And this can be done very efficiently with Wannier functions, as demonstrated by this paper. For example, you can visualize K space distribution of the Berry curvature in a very high accuracy, and you can really see that there is hotspot here and also another hotspot there. Okay, so far we have dealt with insulator, but however, in the previous example, we dealt with BCC iron, which is a metal. In metal, things are a little bit more complicated. Okay, first level, let's have a look at in insulators. Insulators, we have no problem because a set of composite bands here in this window is isolated from the rest of the bands. So it's quite straightforward. We start from, in this example, 8 block functions, and at the end of the calculation, we obtain 9 block function, and we obtain 9 Wannier functions. But for metals, there is no such gap, and always bands are entangled with the rest. So we have to do something to deal with these entangled bands, and a prescription is needed. And this method was developed by Ivo Souza and his colleagues in 2001. And the prescription is now called disentanglement. And it is basically to find a set of block states that are disentangled from the rest of the block states, so that we have, at the end, we have block functions whose number is the same as the number of Wannier functions. And in doing so, we select the smoothest possible subspace, starting from a bit more number of block functions than the number of Wannier functions. I'm going to tell you more detail later. Anyway, once you finish the disentanglement, we proceed for gauge optimization. And this is basically the same as the previous step for insulator. So for disentangling the bands, what you do is first we start with the projection of the initial guess of the Wannier function to block functions. But the number of block states should be larger than the number of Wannier functions. So our idea is that we start from a bit more number of block function and we reduce them to the number of Wannier functions at the end of the calculation. For example, this is the example that I'm going to deal with in BCC iron. So I'm going to cover this range of the energy window, and I'm going to use these Wannier functions to obtain this energy range of block functions to obtain Wannier functions. And there is a notion of outer window. Outer window is basically the energy range covered by these block states, and there are some criterion that you have to think. The first thing is that this window has to be wide so that it includes major weights of the Wannier projection that you are using. For example, if you are projecting S, P, and D as initial projection, S, P, and D character should be included in this energy window. Second, this window should not be too wide. First of all, because it causes a lot of computational cost, but also if your window is too wide, what you get is that some block states far above the energy might have some unwanted character you want to avoid, or there will be some overlap with other block function in the below, and this might lead to some inaccuracy in the disentanglement or difficulty to go through this disentanglement step. It's so difficult to pronounce it. By the way, these n bands can actually depend on k, and you can specify the minimum and maximum of the energy window. And once you project a block function, and what we are going to do is we find an optimal subspace that minimizes the spread. So far, we dealt with only a certain part of the spread, omega d and omega od for insulators. It's because these parts are gauge dependent, so this can be minimized by choosing different u. However, there is another part which is gauge invariant, so that's why I didn't actually introduce this term for insulators. But for metals, because we are choosing the subspace, so even the gauge dependent part can be minimized. So again, what we do is we express this term in terms of k-space expression, and that's what we get at the end with projection operator P and complement of the projection operator in the neighbor points k plus B, and B is a neighbor displacement in k-space, and P is simply a projection operator onto the space defined by the projection. So what is the physical meaning of omega, and what do we get if we minimize omega I? So if you look at this expression, it basically measures overlap between the space we defined at k and the complementary space of k plus b. So what it means is it's an average of the mismatch of the subspace at k and k plus b between neighbor points. So it means that minimizing omega I leads to finding an optimally connected subspace in k-space. So it means that if omega I is small, then our character has very small spillage or leakage throughout the k-space. And to minimize omega I, what we do is we can solve the following eigenvalue problem for this projection operator and iteratively. And I show you this equation to give you an idea of how expensive is the calculation. The computation cost for this step corresponds to diagonalization of this Hamiltonian, whose dimension is the number of block functions. So it's not that big, so it can be done very efficiently. And finally, there is also a concept of the frozen window. The main idea is that sometimes we want to construct finite functions that describe the original bands exactly in a certain energy window. If you are dealing with transport effects, you want your Fermi surface to be exact, for example. So the problem is then we achieve this goal while keeping the rest of the finite functions as localized as possible. How do we do that? And this is introduced again by Ivo Souza's paper in 2001, and it is written in section 3G. To tell you what is done exactly, I mean, not exactly, roughly, we can enforce that certain block states are included in the subspace, and the window, certain window that we define in a way that all the block states are included in the subspace is called frozen window. Sometimes it's also called inner window because it's within the outer window spanned by the block functions. Anyway, so once we include these block states into our subspace, then what we do is that because we have n frozen states already included in our subspace, we are now free to choose the rest of the finite states out of the rest of the block functions. So frozen window has to be somehow optimal, and it has to be not too large and not too small. So if the frozen window is big, then you achieve accuracy up to a certain wide energy range of window. But frozen window is too big, then the disentanglement step doesn't do anything. So you have to compromise between the two. So let's take a look at another example, BCC iron. Here I start from this outer window, spanned by 36 block functions, and I want to obtain 18 finite functions, starting from SPD initial trial orbitals. And I define the frozen window to be +4 electron volt above the Fermi energy. And after the finalization, after the disentanglement and localization, this is the bands that I get from the finite functions. So you see that in the frozen window, the interpolation of the bands is almost ideal, almost perfect, but if you are above the frozen window, there are some deviations. But it is okay because we don't have to calculate anything. It is far above the energy. So again, if you look at closely, the interpolation is really nice and up to the frozen window. So we are guaranteed that if you calculate some physical properties up to this frozen window, what we get is actually quite reliable. So finally, what you can do with FLEUR and Wannier IT. In this tutorial, I dealt with so far very simple examples like lead titanate or iron metal, but you can do a lot more fancy and more complicated stuff. So in principle, you can calculate a lot of Berry phase effect in complicated materials, and in principle, in our group by Yuri Mukursov, most people are working directly or indirectly with Berry phase effects, such as topological orbital magnetism in non-collinear antiferromagnets. And I'm personally very interested in spintronics and orbitronic effects in magnetic devices. And we can also study surface states like orbital Rajba effect. And a few people like Max Merte and Frank Vermus and Todoris, they are working on photo-induced effects like photocurrent or photo-induced spin response and orbital response. And recently we also started to look at 2D materials like transistor metal dichalcogenides or iron germanium telluride or other emerging 2D materials. So I think the only thing left now is for you to try yourself and obtain nice finite functions and use this function for your research and make nice results. Thanks a lot for your attention, and major references are found in these links, in these references. Yeah, thank you.